In this section, we continue infinite series methods, except now we're going to have to do something a little bit different. Let me start with an example to illustrate what I'm talking about. We're going to try to solve the following equation. Using this method of Frobenius. I'll explain the method as we do it. Here, you'll notice that out front of the y double prime is an x. That means that x equals 0 is eliminated from possibility as one of our answers, unless we have some other things in these particular places that will allow us to get around that. The theory will be explained after I do this example. Here's what we do. We set, as before, y equal, not quite to a power series, but something that's related to it. I'm going to have x to the r times the summation k equals 0 to infinity a sub k x to the k. So we're going to have this stuff here, and this x to the r is going to handle the problems that we have around 0. They'll all get shoved into the x to the r. Here we will have a typical power series. Now, like many of the things we do in differential equations, we use x to the r to get an answer, and then we yank the x to the r out at the end, and we have an expression in r. Similar something is going to happen here. So, let me write this in one more format. When it comes to taking derivatives and whatnot, we're going to have to live with the x to the r plus k here for a while. So this is going to be what I set y equal to, and now I have to take derivatives of this in order to plug it into the equation. So let's start with y prime, and this series then we'll start at k equals 0 and go off to infinity. But remember to bring down the exponent, so I have r plus k times a sub k x to the r plus k minus 1. And notice that I'm not starting it at 1. It starts at 0 because r is most likely not going to be an integer. That means that this is not a traditional power series. So it could start with like a sub 0 x to like 1/2, say. Then when you take the derivative, you'll get a sub 0 x to the negative 1/2 times that. And so it will still have a spot in the 0th location. So with that in mind, we're stuck with starting all of these at k equals 0. Take a second derivative. Here we have k equals 0 to infinity, and now I got to take this exponent down. R plus k times r plus k minus 1 a sub k x to the r plus k minus 2. And yes, we're going to plug all of these things into the equation. So our equation then is 2xy double prime plus 5y prime plus xy equals 0. So let me plug these things in now. I'm going to try to do this very slowly, first of all, so that I don't make that many mistakes, and second of all, so that you can hopefully follow the step-by-step details. It does get kind of gory later on, so bear with me and try not to rush through this. So I'll start with plugging in my y double prime. And in this spot then I have r plus k times r plus k minus 1 a sub k x to the r plus k minus 2. And then I have 5y prime, and where did that one go? That was r plus k a sub k x to the r plus k minus 1. And then we had plus x times this stuff. Remember, this equals 0. Now what I'm going to do is multiply these things through and rewrite. So I'll pull the 2x in the first part. And like before, I'm going to put little lines, demarcation lines, to help me out. The first series becomes k equals 0 to infinity. I'll pull the 2 in, so I get 2 times r plus k times r plus k minus 1, a sub k. The 2 I put here, but the x to the 1 power, I'm going to multiply it to this, and that will become x to the r plus k minus 1. I'll suck the 5 into the second series. And then the last series, I'll pull the x in. So that becomes r plus k plus 1. And that equals 0. Now, at this stage, what I'm going to do is I have, if you'll notice, this series here starts when k equals 0, I have r minus 1. When k equals 0, I have r minus 1. But here, when I have k equals 0, I have r plus 1. We'll deal with that in a minute. Let me do some other stuff first. First thing you're going to want to do is factor out the x to the r from everything, because x to the r has already had its effect in the derivatives. So the rest of the stuff will all be contained in the series. So I have 2 times r plus k times r plus k minus 1, a sub k, x to the, now I took the r out, so I have x to the k minus 1, plus the next series, I had k equals 0 to infinity, 5 times r plus k, a sub k, x to the k minus 1, and then plus the last series, a sub k, x to the r plus 1, x to the k plus 1. And that equals 0. Now I'm going to deal with the stuff here where I have k minus 1 versus k plus 1 and things of that nature. And this, if you'll notice, this starts at x to the negative 1, this starts at x to the negative 1, and then this starts at x to the 1. So what we can do is I can reindex these series here, or I can reindex this series. Or, no, actually, no, I don't think I will. I do want to change that. I do want these, however, to catch up to this series. This starts at x to the 1. These series start at x to the negative 1. So I am going to release the first 2 terms from these series. That way, when I do that, all my series will start at x to the 1 power, and then I'll do reindexing from there. So let me get my x to the r out here. You can, for the most part, ignore this thing. It doesn't have any use for the rest of the problem until I write the answer down. This part right here, when I throw in k equals 0, I'll have 2 times r plus 0 times r plus 0 minus 1, a sub 0, x to the 0 minus 1. That's the first term from there. Let me release the first term from here. Plus 5 times r plus 0, a sub 0, x to the 0 minus 1. Now then let me release a second term from each of these series. Then I'll have plus 2 times, now k is equal to 1, so I have 2 times r plus 1, then r plus 1 minus 1, and that's attached to a sub 1 x to the 1 minus 1, plus k equals 1 here. I'll have 5 times r plus 1 a sub 1 x to the 1 minus 1, and then I'll have my series again. And that actually needs to start at k equal 2. And I have already ruined my plans by not having my demarcation lines. Alright, so I have 2 times r plus k times r plus k minus 1 a sub k x to the k minus 1 plus sum k equals 2 to infinity 5 times r plus k a sub k x to the k minus 1 plus the sum k equals 0 to infinity a sub k x to the k plus 1. And that, of course, equals 0. Now, let me go and put my x to the r again, and I'll start a bracket. Here, I'm just going to simplify a little bit to get 2r times r minus 1 a sub 0 x to the negative 1 plus 5r a sub 0 x to the negative 1 plus, and now go through this line here, go through this line right here, and I'll have plus 2 times r plus 1 times r a1 x to the 0 plus 5 times r plus 1 a1 x to the 0. Those x to the 0s really don't matter at all, plus these series. Now what I'm going to do here is I'm going to re-index so that all these start at k, they all start at x to the 1 power, x to the 1, x to the 1. So I'm going to re-index this series right here so that it's compatible with these. That means I'm going to start this series at k equal 2. So these will all start at k equal 2 now. I'll have 2 times r plus k times r plus k minus 1 a sub k x to the k minus 1 plus the sum k equals 2 to infinity 5 times r plus k a sub k x to the k minus 1. And then this one right here, when I started at 2, we have only reindexed to where I would add to the exponent, and I would start this at an earlier number. Now I'm starting it at a later number. So now I have to subtract 2 from each thing that has k. So I'll have a sub k minus 2. It's okay. A sub 0 is a starting point. And then I'll have x to the k minus 1. So actually, I guess this is my bracket here. Let me make this bracket a little more vigorous. Now let me continue this, x to the r. Now for this stuff right here, for the x to the negative 1, let me group these together. A sub 0 x to the negative 1. I'll have 2r times r minus 1 plus 5r, and that will be times a sub 0 x to the negative 1. And over here, these will both be attached to a sub 1 x to the 0. So I'll have 2 times r plus 1 r plus 5 times r plus 1, and that will be attached to a sub 1 x to the 0. The x to the 0 is not important. Now I'm going to get ready to put all of these together into one big series. And I'll just write these all out. 2 times r plus k times r plus k minus 1. That's the stuff attached to a sub k. So I'm going to match it with this stuff. And then that stuff is attached to a sub k. And over here then we have plus a sub k minus 2. And that whole thing forms the coefficient for x to the k minus 1. And that, of course, equals 0. Okay, now let me do a little bit of simplifying here. I have, for this, I'll just multiply it out. I have x to the r times 2r squared minus 2r plus 5r. So 2r squared minus 2r plus 5r is plus 3r. And those are attached to a sub 0, x to the negative 1. Plus, here I have 2r plus 1 times r. So I have 2r squared plus 2r plus 5r plus 5 times a sub 1, x to the 0 doesn't amount to much, and then plus k equal 2 to infinity. I'm going to do something similar here. I notice that I have an r plus k common here, so I'm going to factor it out front. And what that will leave me with is 2 times r plus k minus 1 plus 5. So I'll have 2r, 2k minus 2 plus 5. All that's attached to a sub k. And then we have plus a sub k minus 2. And that stuff forms the coefficient on x to the k minus 1. And this equals 0. Now, notice that these k's start from x to the 1, x squared, x cubed, etc. They go on forever. Here are my initial things right here. We are going to look at a sub 0 as being a non-zero coefficient, but if I'm to have this part inside of the brackets be a power series, then I can't have an x to the negative 1 term. So the only way out of that is to set this coefficient equal to 0. So we'll have 2r squared plus 3r equals 0. So set the coefficient equal to 0 that's attached to a sub 0. This has a name. It's called the indicial equation. This is going to help us solve the whole thing. What we get for r here is going to factor into the rest of the problem. I can factor out an r and leave with 2r plus 3 equals 0, and I get two solutions for that. I get r equals 0 and r equals negative 3/2. I'm going to just box this. Keep it for later keeping. This part right here is where the power series starts. That means here, if you notice, we are going to have k equal 2. I'll have an a sub 2. I'll have an a sub 0 to start with. But if this is the stuff that is attached to a sub 1, then whatever this is, I really don't care. A sub 1 is going to be set equal to 0 because a sub 1 is the coefficient on x to the 1 power. and every coefficient is equal to 0. So with that in mind, this goes a1 equals 0. For this stuff right here, let me do a little simplifying. This part's done and this part's done. I'm just going to focus on this part right now. So I have an x to the r times the summation k equals 2 to infinity r plus k times, inside of here, I'm going to get 2r plus 2k plus 3. That'll be attached to a sub k plus 2. Actually, a sub k, sorry. Plus a sub k minus 2. And all that is the coefficient on x to the k minus 1. And of course, this is all going to equal 0 as well. Every coefficient on x to any whole number power is going to be equal to 0. Now, I'm going to ignore this part. Does not come into play anymore until we get to answer the final problem. However, this stuff inside of here is important for both of these numbers. Let's start with r equals 0. If r equals 0, let me remind you, I'm going to set all of this coefficient equal to 0. If r equals 0, then r plus k is just k. And then 2r is 0, and so I get k times k plus 3, a sub k plus a sub k minus 2 equals 0. And this is where I'm going to start finding my coefficients. Solve for a sub k. That equals negative 1 over k times 2k plus 3. Just notice an error there. A sub k minus 2. And now this series starts when k equals 2. So my k's will start at 2. K equals 2. I'll get a sub 2 equals negative 1 over 2 times, when k is 2, this part will be 7. A sub 0. Then when k equals 3, I'll get a sub 3 equals negative 1 all over 3 times 9 a sub 1, but a sub 1 is equal to 0. In fact, I hope you'll find out that all the odd ones will end up being 0, because my next one will be a sub 5 in terms of a sub 3, and that will be 0. So I'll get no odd ones at all. Let me go k equals 4. A sub 4 equals negative 1 over 4 times 2 times 4 is 8, 11. A sub 2. But a sub 2, of course, I can rewrite in terms of a sub 0 with a negative there. The negatives will cancel, and it looks like I'll have 1 over 2 times 7 times 4 times 11. So I have 2 times 4 times 7 times 11. Remember, I do this in case a pattern should happen to emerge. K equals 5. We have a sub 5, of course, equals 0, since it's dependent on a sub 3. K equals 6. A sub 6 equals negative 1 over 6 times 2 times 6 is 12 plus 3 is 15. A sub 4, and that will equal negative 1 over 6 times 15. A sub 4 was this stuff here, 1 over 2 times 4 times 7 times 11, a sub 0. And if I wanted to, I could simplify this a little bit, I suppose. I could even think of 15 as 3 times 5. I don't exactly know how that would help me out. I'd have 2 times 3 times 5, but then you have 2 times 3 here also. And I'm not sure if that would help me out. Let me just write it negative 1. I'll write it in order, though. I'll have 2 times 4 times 6 times 7 times 11 times 15, a sub 0, and you can see that it's growing very fast. K equals 7. We've already told you that a sub 7 will equal 0. And so I think I have enough terms right now to write out my answer. So one solution is a sub 0. A sub 0, now don't forget that this was attached to x to the r. And this was when r was equal to 0. So I'll get x to the 0, which it doesn't matter, I understand that, but I'm putting there for cataloging purposes. Since we started a sub 0, we're going to get 1 where the a sub 0 spot was. Now then my a2 is attached to x squared, so I get negative 1 over 2 times 7 x squared. And then x to the 4th, I get 1 over 2 times 4 times 7 times 11. And I have x to the 6th. And these coefficients are going to grow out of hand very quickly. And that's one solution. So in fact, we can think of a y1 equal to 1 minus 1 over 2 times 7 x squared plus 1 over 2 times 4 times 7 times 11 x to the 4th minus 1 over 2 times 4 times 6 times 7 times 11 times 15 x to the 6th plus dot dot dot. And remember, y1 is the particular part of the solution. A sub 0 is merely a constant. Now, there was one solution. Let me go ahead and demark. Now, another answer that we had was that r equals negative 3 halves. We had 0 and negative 3 halves were the roots of our initial equation. So here we are going to have different numbers here. Instead of these, r equals 0 made this a lot easier. But now when r equals negative 3 halves, this is going to be a little bit of a different story. So let me go ahead and copy this down and bring it below. So it's the same deal as before, except now my r is going to be replaced with negative 3 halves. So I get negative 3 halves plus k, 2 times negative 3 halves plus 2k plus 3, a sub k plus a sub k minus 2 will equal 0. And let's go ahead and simplify as much as I can here. For some reason, I like to rewrite the first one as k minus 3 halves. For this, notice the 2's cancel here, and we end up with negative 3 plus 2k plus 3 a sub k plus a sub k minus 2. That's equal to 0. Some nice things happen here. If you look, 3's cancel, and I'll have a 2k. If I take this 2 and put it to here, I can get this to be 2k minus 3 times k, a sub k, plus a sub k minus 2 equals 0. And then when I go to solve for a sub k, I have a sub k can equal negative 1 over k times 2k minus 3, a sub k minus 2. And now I can go ahead and get my coefficients just like I did before. I can start with k equals 2. That's where the series started, when k was equal to 2. So I'll have a sub 2 will equal negative 1 over 2 times 2 times 2 is 4 minus 3 times 1, a sub 0. K equals 3. I will get a sub 3 will equal negative 1 over 3 times, if I put a 3 in here, I'll get 6 minus 3, 3 a sub 1, although that was 0. So same thing's going to happen before. When a1 is equal to 0, it's going to affect no matter what the r's were. K equals 4. I get a sub 4 equal negative 1 over 4 times 8 minus 3 is 5. A sub 2. And a sub 2 was negative 1/2 a sub 0. So I'll get 1 over 2 times 4 times 5. A sub 0. K equals 5. A sub 5 will equal 0. All the odd ones will be 0 as before. Don't believe that always happens. This is just, in this particular example, is why that happens. Then we get K equals 6. I got a sub 6 equals negative 1 over 6 times 2 times 6 will be 12, minus 3 will be 9, times a sub 4. And a sub 4 was 1 over 245, so I'll throw those in. Negative 1 over 2 times 4 times 5 times 6 times 9, a sub 0. And then you get the idea. K a sub 7 equals 0. And this, of course, goes on. So if you will, my y2 then is going to be, here we have x to the negative 3 halves. That's where the r, x to the r, was out front of all this stuff. And then, once again, since it starts at a sub 0, I'll get a 1. And then my a sub 2 will be negative 1/2 a sub 0, or negative 1/2 x squared. A sub 2 is attached to x squared. A sub 4 is attached to x to the 4th. And then for my x to the 6th term, I'll have negative 1 over 2 times 4 times 5 times 6 times 9, x to the 6th, and plus dot dot dot. Then our answer, of course, y equals c1 y1 plus c2 y2. And the c1 and c2, those were a naughts. It really doesn't matter. They could be different things. It really doesn't, because I'm doing it for 2 different r values. And so, well, I'll just leave it at that. Now, let me talk a little bit about the theory. The type of equations we're solving are like these. Now, a lot of things are contingent upon this leading coefficient here, this a2 of x. Most likely these will all be polynomials, and this will all work out nicely. Suppose a2 of x sub 0 equals 0. Well, if now pretend I am talking about polynomials, since all this will make sense then. Then x minus x sub 0 is a factor of a2 of x. And we could write, if that's the case, then a sub 2 of x can be factored as x minus x sub 0. Now, when I say x minus x sub 0 is a factor, it may be like a factor n times or whatever. I may be able to factor out, I'll say n sub 2 of it. So this is going to be some sort of a natural number up here. And the stuff that's left over, let's call it p sub 2 of x. And this will be a polynomial that's left after factoring out all of the x minus x sub 0 that I can. Now, the first thing you're going to do is you're going to divide by that thing when solving these types of equations. So I'll get a sub 1 of x all over a sub 2 of x y prime plus a sub 0 of x all over a sub 2 of x y. Now, it's possible that x sub 0 happens to also be a 0 of a sub 1 and x and of a sub 0. So let me make the assumption, not an assumption, just let me write this as x minus x sub 0 to the n1 p1 of x, and then I'll replace this with this factorization here, x minus x sub 0 and 2 p2 of x y prime plus x minus x sub 0 n sub 0 p sub 0 of x all over x minus x sub 0 n2 p2 of x times y equals 0. Now these are factored in such a way that x sub 0 is not a 0 of p1, x sub 0 is not a 0 of p2. So I factored out as much x minus x 0 as I can from everything. Same thing here. So I can rewrite this in the following fashion. Now, the way the theory works is this. We're not going to prove any of this stuff per se, but you need to check these things to make sure that you can proceed with such a solution. Here, what we need n sub 2 minus n sub 1 to be less than or equal to 1, and we need n sub 2 minus n sub 0 to be less than or equal to 2. So when I factor that out, I'll get something like that. If these two conditions are met,